Hello, NEET aspirants. Welcome to our exploration of buoyancy and Archimedes guideline. We often see the objects floating or sinking in liquids in our daily life. Like when we pull something out of well, ever wonder why it is easier to sink in the water than lift it out? Let's explore and understand why this happens in this video. As we immerse an object in liquid, it experiences an upward force called buoyancy. Objects float because the liquid they displace exert an upward force equal to their weight. It is like the liquid saying, "You belong to up there." Now, let's get into the math. Imagine a beaker of water. The pressure in the liquid affects in all directions, not just downward. In a static system, like a submerged object, the pressure is uniform in all directions. Think of it as a silent orchestra of forces. Let h is the height of the object sink. Rho is the density of the liquid. A is the surface area of object. The pressure at top and the bottom will be different due to the effect of gravitation, and Pb, that is the pressure at the bottom, is greater than the pressure at top. Now, Pb is equal to G into bracket H plus D bracket close into rho into A, and Pt is equal to G d rho A. To get a handle on the net force on the lowered item or sinked item, we should imagine a shape submerged. As earlier, the pressure difference on the solid shape base and the top, that is Pb, is greater than Pt, result in net force numerically communicated as Fn is equal to G into bracket H plus D bracket close into rho into A minus G d rho A. On simplifying, we get Fn is equal to G rho into H into A. This is interesting because HA represents the volume of the cube. As a result, the formula of the net force is equal to Fn is equal to G rho into volume of a liquid displaced, or we can say it as Fn is equal to weight of a liquid displaced. The net vertical force we examined is the buoyant force. At the point when an object is lowered, it encounters a buoyant force equivalent to the weight of the liquid is displaced. This force is the cause behind why item can effortlessly float or delicately sink. If the weight of the immersed object is greater than the weight of a liquid displaced, object sinks. If the weight of the immersed object is less than the weight of a liquid displaced, it floats. If the weight of the immersed object is equal to the weight of the liquid displaced, object do not sink or rise, or we can say it remains at a particular position where you have placed. The net force acting on the object is Fg, that is the gravitational, minus Fb, that is the buoyant force, which can be represented as m into G dash. Here, G dash is the resultant gravitational acceleration, can be represented as is equal to G into bracket 1 minus rho of object divided by rho of liquid. Here, rho is the density, expression for immersed volume of a floating body. Let solid of volume V and the density rho floats in a liquid of density rho L. Volume V1 of the body is immersed inside the liquid. The weight of the floating body is equal to V rho G. The weight of the displaced liquid is equal to V1 rho L into G. For the body to float, weight of the body equals to weight of a liquid displaced. Therefore, V rho G equal to V1 rho L into G. On simplifying it further, we get V1 is equal to V rho upon rho L, as V into density is equal to mass of the object. Therefore, V1 is equal to mass of an object divided by density of fluid. Now that we have investigated Archimedes guideline, how about we dive into unpredictable dance between center of mass COM and center of buoyant force COB, revealing insight into the steadiness of lowered object or drifting object. Picture this. When a center of mass and a buoyancy align vertically, a floating or submerged object achieves stability. The center of gravity of the displaced liquid COB lies vertically above or below the center of gravity COM. Object floats is stable. Imagine it as a ballet where the partners buoyant force and the dancers the object moves in perfect harmony. However, in the event that the object slants or tilt, making COM and COB head out in different direction on the level plane, force arises. This force goes about as a gatekeeper trying to re-establish harmony. It is like to the infinite dance where irregularity triggers vast powers to realign. Imagine a ship is sailing through a sea. When the center of mass and the buoyancy are in line, the ship stays stable. Due to strong waves, ship tilt, a buoyant force pushes it back to stability. This happens not just in physics but also in everyday situation. Cells uses buoyancy-like forces to maintain their shape and move within the liquid. This is crucial for the functions in the body. Now, we will solve some interesting problems based on the Archimedes Principle and buoyant forces. A stone of mass 0.3 kg and its relative density is 2.5 is immersed in a liquid of a relative density 1.2. Asked to calculate the resultant upthrust exerted on the stone by the liquid and the weight of a stone in the liquid. Let's solve it. Volume of a stone V is equal to mass upon density. Therefore, V is equal to 0.3 divided by 2.5 equal to 0.12 meter cube. Upward thrust is equal to buoyant force. Therefore, V rho Lg is equal to 0.12 into 1.2 into 9.8 is equal to 1.41 newtons. The weight of a stone in liquid is equal to gravitational force minus buoyant force equals to 0.3 into 9.8 minus 1.41. On simplifying it, we get 1.53 newtons or 0.156 kg weight. Problem 2. Imagine a metal cube floating on the mercury with 1/8 of it under the mercury. If we add enough water to cover the cube, what part of the cube will stay under the mercury? After adding water, now let V dash be the volume immersed in mercury, then V minus V dash is the volume of an object immersed in the water. Then weight of a metal is equal to buoyant force due to water plus buoyant force due to mercury. On substituting the relative values, we get V into bracket 1.725 bracket close into G equal to into bracket V minus V dash into 1 into G plus V dash into 13.6 into G. On simplifying it further, we get V dash is equal to 0.725 divided by 12.6, which is approximately equals to 1 upon 18. Thus, only 1/18th of volume of the cube is under mercury. Problem 3. A block of ice is floating in beaker. When the ice melts, then what will be the level of water? When a block of ice is floating in a beaker, it displaces its own weight of water. This is due to the Archimedes Principle, which states that the buoyant force on an object immersed in a liquid is equal to the weight of the fluid displaced by the object. As the ice block melts, it turns into water, but the water it turns still has the same weight as the ice block. Since the buoyant force remains the same, the water level in the beaker will not change as the ice melts. In summary, when the ice block floating in a beaker melts, the water level will stay the same. Problem 4. In alloy of gold and copper, weights 0.2 kg in air and 0.188 kg in water. The densities of gold and copper are 19.3 into 10 raised to 3 kg per meter cube and 8.93 into 10 raised to 3 kg per meter cube respectively. Asked to find the amount of gold in the block. Now we will do it 2 steps. Step 1. First we will calculate the volume of the block. Loss of weight is equal to weight of water displaced. Therefore, 0.2 minus 0.188 is equal to volume into density of water. Therefore, 0.012 is equal to V into 1000. The volume of alloy becomes V is equal to 12. Volume of the alloy is equal to 12. Step 2. Now we will define variable and find the volume. let M equal to mass of the gold. Therefore, volume of a gold is equal to mass upon density equals to M upon 19.3. Mass of a copper is equal to 200 minus M. Therefore, volume of a copper is equal to 200 minus M divided by 8.93. Now we'll go for the final step. Equation for the total volume. The volume of a copper plus volume of a gold is equal to volume of alloy. Therefore, 200 minus M divided by 8.93 plus M upon 19.3 is equal to 12. The equation what we got is 200 minus M divided by 8.93 plus M upon 19.3 is equal to 12. On simplifying, we get M is equal to 0.112 kg is the mass of the gold in 0.2 kg of block. So, we bring our exploration of Archimedes Principle and the Law of Flotation to close. In our next video, we will delve into the fascinating world of fluid dynamics and Bernoulli's equation. Before I, Avinash from Janet.com sign off, I kindly request you to share and subscribe to our channel. Until then, continue to go with the flow and immerse yourself in the knowledge of the law of nature. Thank you for joining us on this journey.